Hi everyone, welcome back to my YouTube channel. Today's video is a continuation of what we discussed in last time. So if you have not seen that previous video, please make sure to see that video. Then only you can understand the concepts very clearly. And before going to start the video, please do subscribe to my YouTube channel and make sure to share this video with your friends, like and comment below. In last video we discussed up to 4 topics and now we will discuss remaining topics. So the first topic in this video is describe the intrinsic semiconductors and Fermi level. So what is meant by intrinsic semiconductor? See, a pure form of semiconductor is called intrinsic semiconductor. So these intrinsic semiconductors is also called undoped semiconductor. Remember this point, it is very important. That is, a pure form of semiconductor. Pure semiconductors is also called undoped semiconductors. There are different types of example, but majorly we are using mostly two, that is silicon and germanium. So in pure form of semiconductors, the electrons are equal to the holes. Means equal number of electrons and holes are presenting in the pure form of semiconductor. So why it has equal number of electrons and holes, I will discuss later in this video. And now this silicon or germanium will form the covalent bond by sharing the electrons to the neighbors. And here there is a small mistake. It has 4 valency electrons but not 8 valency electrons. So just here replace it. So it has 4 valency electrons. So at room temperature, these valency electrons break the covalent bond. After breakdown of the covalent bond, the electrons will move from the valency band to conduction band. In the place of electrons, the holes will be created. That and electrons will move from the valency band to conduction band. Then only it will conduct. And we apply electric field to these intrinsic semiconductors. So the current conduction is occurred due to both electrons and holes. So the total current inside of the semiconductor is the sum of current due to free electrons and holes. Now we will see the crystal structure of pure semiconductor and energy band diagrams, and we will see what happened if we apply some electric field to that intrinsic. Here I am showing the crystal structure of silicon. So here I am considering 3:3 ratio, but that is your choice. We can consider 4:4 or we can consider 5:5. So here I am drawing the silicon structure by using 3:3 ratio. So what is this means? So that is the atoms with silicon. Silicon means here the bond will be forming in between the two neighboring silicon silicons, right? So and this silicon has 4 valency electrons in its outermost shell, that is we know. So these electrons will make covalent bond with the neighbor atoms. When this covalent bond break means at room temperature, this covalent bond will be broken. After the breakdown of the covalent bond, the electrons will move from the valency band to conduction band. Means before moving, after the breakdown of the covalent bond, the free electrons will be occurred. That free electrons will move from the valency band to conduction band. In place of free electrons, that holes will be created. So the Fermi level means we know in the intrinsic semiconductors, the current conduction is due to both electrons and holes. That's why this Fermi level will lies in between the valency band and conduction band. So that is free electron. Now we will see what will happen if we apply some electric field to the intrinsic semiconductors. So here I am drawing one junction, that is So I am applying some external field, and these are the whole electrons, and down these are the electrons. So we know everywhere the opposite polarities will be attract, means we know electrons has negative charge and holes has positive charge. So these electrons will attract towards the positive terminal. Coming to holes has positive charge, right? So that is attracted towards the negative charge. That's like the current conduction will be done due to both electrons and holes. So in intrinsic semiconductors, we have to remember some main important points. So in intrinsic semiconductor, there are equal number of electrons and holes, and at room temperature, the covalent will be broken and move from the valency band to conduction band. The current conduction is due to both the electrons and the holes. So our next topic is describe the extrinsic semiconductors and their energy band diagrams by using the Fermi level. So what is mean by extrinsic semiconductors? We already have the intrinsic semiconductors, right? So but why we are shifting from intrinsic semiconductors to extrinsic semiconductor? First thing, what is mean by extrinsic semiconductor means, see, by adding impurities to the pure form of semiconductors, that is called extrinsic semiconductors. So in the intrinsic semiconductors, we have poor conductivity. Why? Because the bond will be formed in between the covalent bond. There is no free of electrons, right? So the conduction will be done after the breakdown of that covalent bond. Then only the conduction will be done. That conductivity also very low. That's why we can easily neglect. So to improve the conductivity, so this is the main point. That's why we are using the extrinsic semiconductors. To improve the conductivity of the semiconductors, the doping will be done. Doping is nothing but adding impurities to the pure form of semiconductors. So by adding impure semiconductors, the free electrons will be there. That's why the conductivity will be increased. So these extrinsic semiconductors are also called impure semiconductors and doped semiconductors. So I already told what is meant by doping. Doping is nothing but adding pure impurities to the pure form of semiconductors. By adding impurities, that will convert from the pure semiconductors to impure semiconductors. That is called extrinsic. We are adding two types of impurities. There are two types of impurities in the extrinsic semiconductors, that is n type or donor type, that is from pentavalent, and our second impurity is p type semiconductor, that is called acceptor semiconductor or from trivalent. So these types are often due to the type of impurities added to the pure semiconductors. See here, you can get some clarity. So in pure form of semiconductors, we have only 4 valency electrons. So that 4 valency electrons will form the covalent bond. So this covalent bond is broken when at room temperature. After the breakdown of the covalent bond, the free electrons will be obtained. That free electrons will move from the valency band to conduction band. So by then only they will conduct, and this conductivity is very low. To improve the conductivity, we are adding some impurities. So what will happen, we adding some impurities means the conductivity will be improved. How the conductivity will be improved means, impurities are added to improve the conductivity. So these impurities will having the more number of electrons, that's why free electrons will be obtained. The conductivity will be increases. So there are, we know, two types of impurities are there, that is from fifth group and third group elements. These fifth group elements is also called as the n type, that is pentavalent. Fifth group means pentavalent. Third group means trivalent, that is p type, and that is called acceptor. See here, fifth group has 5 valency electrons, right? And third group has 3 valency electrons. These 5 valency electrons in pure semiconductors have 4. So here 4 and here 4 will be form covalent bond, and one free electron will be obtained. So that free electrons will improve the conductivity. Coming to the third group element, we have 3 3 and they will form covalent bond and one will improves the conductivity. Now we will see the in detail n-type and p-type semiconductors. N-type semiconductors. So in n-type semiconductors we are adding pentavalent atoms, means we are adding impurities from the fifth group elements. Fifth group elements are phosphorus, sulfur, arsenic. These are all belongs to the fifth group elements. When we add these impurities to the pure form of semiconductors like silicon or germanium, that is called n-type semiconductors. Adding impurities to the pure semiconductors, that impurity is belong to the pentavalent, means fifth group elements, that is called n-type semiconductors. See, in n-type semiconductors there are 5 valence electrons, right? In pure they have 4. So from the n-type semiconductor, and silicon has 4. So these 4 will form the covalent bond, and there is no chance to fifth valency electron impurity atom to form the covalent bond. So at room temperature, this free valency electron gets some energy, and that free electron will enter into the conduction band. So this electron impurity provides or donate the electron to the conduction band. So it is donating electron to the conduction band. That's why it is called donor. N-type semiconductors are called donors. After donating electron to the conduction band, that impurity electron will form positive ion. Remember this, after donating the electron to the conduction band, will be formed like positive ions. So after that, at room temperature, the covalent bond will be broken and generate the free electrons and holes. So it will move from the valency band to conduction band. So in n-type semiconductors, in the place of free electrons will move from to the conduction band. In place of that electrons, holes will be created. And coming to the conduction band, there are more number of electrons when compared to the here holes. Why? Because already one electron donated to the conduction band. After that, some breakdown free electrons will be also go to the conduction band. Like that, the electrons will be more in the n-type semiconductors. Now we will see the crystal structure of n-type semiconductors, and also we will see the energy band diagrams, and we will see the the crystal structure of n-type semiconductors means, n-type semiconductors, what are the pentavalent elements means, when we see the periodic table, there are fifth group elements that we can consider as pentavalent. So now I am considering phosphorus. See, in the middle of the structure I am considering phosphorus, that with 5 valence electrons. Surrounding them I am considering the silicon as semiconductor. So I am forming a bond between the phosphorus and silicon, right? See, here I also considering 3:3 ratio. So that is your choice. You can consider 4:4 or you can consider 5:5 ratio. See, this phosphorus has 5 valence electrons that we know, and coming to silicon, it has 4 valency electrons. See, here one electron will be left over, that is known as the free electron, and we know silicon has 4 valency electrons, so the bond will be created, and here the one free electron will be left over. That electron is known as the free electron. So what I am told means, so when the electron will donate to the conduction band, that will form the positive immobile ion, that is positive immobile ion, and here electrons are more when compared to the holes. That's why here showing more electrons when compared to the holes. So now we will see the Fermi level. So Fermi level means here the electrons are more when compared to the holes. That's why the Fermi level will shift towards the conduction band. So I hope you understand the concept. So some main points we have to remember according in n-type semiconductor means, in n-type semiconductor we are adding fifth group elements, and here electrons are majority, holes are minority. So means electrons are more when compared to the holes, and the current conduction is due to electrons. The Fermi level is towards the conduction band. So this is the n-type. Now we will see the p-type semiconductor. So this p-type is also same as the n-type, but there is a small difference. In n-type we are adding pentavalent atoms, means we are adding fifth group elements to the semiconductor. Now in p-type we are adding trivalent atom to the silicon. Trivalent means third group elements, that is like boron, indium, gallium, etc. are added to the semiconductor silicon and germanium, that is known as the p-type semiconductors. Adding third group elements to the pure semiconductor, that is silicon or germanium, that is called p-type semiconductors. So in p-type semiconductors means in trivalent they have 3 valency electrons, right? So these will form these 3 valency electrons with neighbor atoms, and fourth covalent bond will be unable to bond. So why? Because here there is no vacant space is created for the fourth covalent bond. There is a vacant space, that space is called hole. So here the hole has more tendency than the electrons. So in p-type semiconductors we have more holes compared to the electrons. So has chance to accept the electron. So that is known as the acceptor. On room temperature the covalent will be broken and it will move from the valency band to conduction band. Here the holes are more when compared to the electrons. So now we will see the crystal structure of p-type extrinsic semiconductor. So the crystal structure of p-type semiconductors is shown in below figure. Here I am considering boron as example of the trivalent, and remaining are the silicon or germanium. I am considering as silicon. So we know the bond is formed between the boron and silicon. Here I am considering as 3:3 ratio. You can consider your wish. And the bond here we have 3 valency electrons for the boron and 4 valency electrons for the silicon, right? So the bond will be formed in between that, but there is no space to form a bond for the fourth valency electron. Means there is no electron in that place. The hole will be created. So that hole is created, and this is the trivalent. Now that hole is presenting in the valency band. So here after the breakdown of the covalent bond, the electrons will move from the valency band to conduction band. In place of that electron, the holes will be created. Here there are only 4 electrons and we have 5 holes, right? So we have 5 holes in the valency band. That's why the holes are majority when compared to the electrons. So the current conduction will be done due to the holes. So the Fermi level is towards the valency band. Here why I am showing negative immobile ions means by accepting electron it will form the negative immobile. That's why I am showing here as the negative immobile. Now we will see the major difference between the intrinsic semiconductors and extrinsic semiconductors. As we know, intrinsic semiconductors are also called as the pure semiconductors or undoped semiconductors, and extrinsic semiconductors are also called impure semiconductors or doped semiconductors. And our second point is, at room temperature the number of electrons are equal to the number of holes. And coming to the extrinsic semiconductors, at room temperature the electrons are not equal to the holes. At 0 degree Kelvin the temperature, there is no free charge carriers are not available, and the valency electrons will be participated in the covalent bond. Coming to the extrinsic semiconductors, there are free charge carriers are available at 0 degree temperatures. So coming to the energy band diagrams, the Fermi level lies in between the valency band and conduction band. So coming to the extrinsic semiconductors, we know there is 2 types, that is p-type and n-type. Coming to the n-type, the Fermi level lies towards the conduction band. In the p-type, the Fermi level lies towards the valency band, and in intrinsic semiconductors the current conduction depending upon the temperature. Coming to the extrinsic semiconductor, the current conduction depending upon the amount of doping and amount of impurities added. For example, when we add n-type semiconductors, the current conduction will be done due to the electrons. Coming to when we add p-type impurities, the current conduction is due to holes. Why? Because the majority charge carriers. Based upon the majority charge carriers only, the current conduction will be done. And so we know less conductivity in the intrinsic semiconductors, conductivity is more in extrinsic semiconductors. To improve the conductivity, we are using these extrinsic semiconductors. Examples for the intrinsic semiconductors is silicon or germanium. And coming to the extrinsic semiconductor examples, n-type and p-type semiconductors. Like coming to the p-type, it has boron, iridium, and coming to the fifth group elements, that is phosphorus, etc. This is the major difference between the extrinsic semiconductors and intrinsic semiconductors. I hope you understand the concepts very clearly. If you learn something new in this video, please do subscribe to my YouTube channel and don't forget to share my video with your friends who require this video. Thank you for watching. Let's meet in next video with some other topics.